Okay, so the good news is if you can make it through till 3:30 today, then the rest of the course will be very easy and very pleasant. The bad news, of course, is that's still 6.5 hours away. So anyway, today, most of today is on learning how to run this Hydrolight software. So I'm curious, how many people have never heard of Hydrolight till you got here? Okay, so that's like 3 or 4. How many people have heard of it but never used it? That's most of the people. How many people have already been using it for? And so there's a couple people there. So that's kind of standard. Okay, so anyway, Hydrolight is software that solves the radiative transfer equation and computes the underwater radiances and irradiances and all the reflectances and K functions and all of those things for whatever input you give it. So you're going to have to give it the absorbing and scattering properties of the water, where the sun is in the sky. If it's finitely deep water, you know, what's the depth, what's the bottom reflectance, all of those kinds of things. And so that's what we're going to learn how to do today. And then you click the button and it solves this radiative transfer equation, which we haven't talked about because that's a whole lecture in itself, and we just don't have time to sort of derive it, but basically you will take a quick look at it. And then you get out various output files, printout, and files that are made to open in Excel spreadsheets and things like that. So we'll see how all of that works. And then in the practicals, after I get done this morning, I'll pass around CDs with Hydrolight on it, and you can install it. And we'll talk more about this, but basically the standard version that I have here runs only on Windows computers, Microsoft Windows. But John Headley has been working to develop Apple and Linux versions, so he has an Apple version which we'd like to actually try out on somebody for the first time. And then even if you have a Windows computer and you don't have a CD drive, well, you know, then you can't install it, so because it's only here on CD. But I encourage you to work together. So find somebody that has a Windows computer or an Apple computer, and you know, just work with them, because this is just to learn about it. It's not, you know, an exam for each individual person. So anyway, we'll do that at the break. I'll pass these around and we can start installing them. I also brought copies of the Light and Water textbook, which you can download from the web, but if you want to take this and just copy the whole thing over, you're welcome to. I also brought one copy of this almost 2,000-page book by Rudy Preisendorfer. If anybody wants this, you're welcome to copy all of this over. It's like 200 megabytes, and it's old notation, it's very mathematical, but it's all there. So he was one of the gods of the field, and you can also download this from the Ocean Optics web book, but it probably takes an hour because there's so much stuff. So if anybody wants to, you know, borrow these, copy it over, that's fine, and then we'll spread these around. Okay, so let's just get started then and take a look at what Hydrolight is. So with any software that solves the radiative transfer equation or does anything else, there's usually a physical model, that is, what problem are you solving physically. There's a computational model, which is how do you actually do that, and then we'll talk also about, you know, how do you actually use this thing. I'll say a little bit about the software, and then I'll do some example runs and kind of show you how to do everything, how to look at the output, and then we'll install the code, and I'll have a series of little exercises that you guys can do just working on together and you know, learn more about it. And then of course you're welcome to keep running it for the rest of the class. Okay, so here's this radiative transfer equation, and really the radiative transfer equation is just conservation of energy expressed in terms of radiance. So what it says, and if you go to the Ocean Optics web book, there's a page called Deriving the Radiative Transfer Equation that sort of looks at, you start out with a light beam and it could get absorbed and more could get scattered in, and it light can get scattered out, and there can be an internal source and so on. So that's just a quick way to think about things. But basically, if you write it out, we're going to solve for the radiance as a function of depth, direction, and wavelength. And you end up with this big, nasty looking equation. It's called an integral differential equation. So there's a derivative and there's an integral. And it says, okay, the depth rate of change of the radiance in a particular direction, theta phi, at a particular wavelength. Well, how does that change with depth? Well, the radiance that's, let's say, starting up here, and it's going to come through the water in this direction. Well, what can happen to it? Well, it can be absorbed and we lose radiance, so a negative sign, or it can be scattered into some other direction that we're not looking at and we lose radiance due to scattering, or radiance from some other direction can be scattered into the direction I'm looking at. So I have a term here that is the radiance in all directions being scattered into the direction I'm interested in. So this is the scattering phase function, or the scattering coefficient times the scattering phase function is the volume scattering function. So basically there's a term that is then a gain of radiance in my direction, theta phi, from radiance in other directions being scattered into that direction. We integrate that over all solid angle, over all directions. And then there might be an internal source like bioluminescence, for example, that's creating new light in the direction I'm looking at. So that's the equation that Hydrolight's going to solve. And then you have to have some boundary conditions as well, and those are things like where the sun is. The game we're playing is we're going to put in the things that are underlined in green. So here's IOPs, and here's a source term. There's the phase function. And then we're going to solve this equation for the things that are underlined in red, which is the radiance. So, we have to know the IOPs, we have to know the internal sources, we have to know the boundary conditions. And then Hydrolight computes the radiance as a function of depth, direction, and wavelength. And then from that radiance, it computes all the irradiances and K functions and reflectances and all of those things, just using their definitions that we looked at the other day. Okay, just to make a comment here, the only thing that goes into the radiative transfer equation is the total absorption, the total scattering. The light doesn't care whether this absorption came from CDOM or a phytoplankton or a water molecule or what. It just says I got absorbed or I didn't. So it's only oceanographers that care how much of the absorption is due to these different components, because that's telling you something about how the ocean works. But the light field just says, no, give me the total, I'm happy. And so when you run Hydrolight, as we'll see, we'll generally build up these by putting in how much chlorophyll's in the water, how much CDOM, how much minerals, how many bubbles, etc. But Hydrolight then just takes all that and adds it together and gets a number, and away it goes. Okay, so in order to solve the radiative transfer equation, what you always have to have is a region of interest, and this could be the ocean, it could be a cloud, but you know the IOPs, the absorbing and scattering properties within the region, and you know the radiance onto the region from outside. And then there's a unique solution to the radiative transfer equation with some horrible mathematical theorem by a bunch of Russians that actually proved it does have a solution. Now that's their view of it. My view of it is, you know, it has a solution because light propagates through water. And I didn't have to do the math to do that. Okay, so what Hydrolight does is it just takes what's generally a three-dimensional problem and it sort of stretches out the region and makes a horizontally homogeneous ocean where things can vary with depth but not horizontally. So you have the same sunlight onto the surface. You have, if there's a bottom, it has to be level. It can't be sloped, because that's really then a three-dimensional problem. So it turns the more general problem into a one-dimensional problem, namely things vary with depth but not horizontally. And then the model, the way it's all set up is it's going to be time independent. So think of going out and you make, let's say, light measurements for 5 minutes, and any waves or anything that come along, they all average out, and you're just getting this 5-minute average of the light field. Things that can depend on depth. Everything, the light field always depend on depth, but the IOPs can as well. Now, there are techniques that break the water column up into a number of homogeneous layers. That's not the way the math in Hydrolight works. You can have whatever depth profile of IOPs you want. There's no restrictions on wavelength. In the standard version, you have that you can run it from 300 to 1,000 nanometers. The very most recent version allows you to solve for any wavelengths if you have the needed inputs. So if you want to run Hydrolight down to 200 nanometers, you can, but then you have to know, well, what's the phytoplankton absorption and scattering and all that at 200 nanometers? I have no idea. It's never been measured. So it's up to you to define those inputs, but we're not going to do that in here. You can have any distribution of sky radiance onto the sea surface. The waves on the sea surface in the current version are parameterized by what's called the Cox-Monk wind speed wave slope statistics. So you basically were going to put in the wind speed and it's going to make the surface rough, or if the wind speed is 0, the surface is level. There's various bottom options. You can have infinitely deep water, you can have finitely deep water, but with some specified bottom reflectance and so forth. There are a lot of techniques like Monte Carlo techniques where you sort of trace a photon and it bounces around, and then after maybe 3 interactions, you don't bother to trace it anymore. And in Hydrolight, the math automatically solves for all orders of multiple scattering. So there's nothing like a single scattering or anything. It's all there. We won't go into the math, but that's one of the features of this technique called invariant embedding theory that Hydrolight uses. Is instead of computing a light field term by term, if you wish, single scattering plus 2 scatterings plus 3 scatterings, you actually solve for the infinite series all at once. There are inelastic scattering effects like Raman scattering by water, fluorescence by chlorophyll and CDOM, and you can include those or you can leave them out, but they're in there. You can have internal sources like bioluminescence, but keep in mind it has to be a horizontally homogeneous like layer of bioluminescence, which you do get in the ocean, in places like the Arabian Sea especially. So you can't have a point source of bioluminescence. The biggest inaccuracy in Hydrolight is that it does not include polarization. And so generally, if you look at the radiances in Hydrolight, and if you look at this direction, maybe the radiance is 10 or 15% too big. If you look at that direction, it's maybe 10 or 15% too small. And that's because polarization is out there in the real world, but when you compute something like an irradiance, you're averaging over all directions. So this being a little big and that being a little small tends to average out, and your irradiances will be maybe good to within 1%, even though the radiance in a particular direction is maybe only good to 10 or 15%. So that's not a big problem. And then things like apparent optical properties, which are usually ratios of irradiances or something, they're also perfectly fine, even though polarization's not there. And then the sea surface model doesn't have things like white caps, but that's generally a minor problem. Okay, so this code has been around now for as a commercial product for over 15 years, and there's been, hundreds and hundreds of papers published with Hydrolight. There's over 200 people have licenses on, every continent except Antarctica. So anyway, it's been around a while, and I've finally gotten over being afraid that there's like a factor of 2 or a minus sign error or something in the code. So it seems to be putting out the right answer. So that's the physical model. So computationally, the way it works is if you think of all directions here, and we're going to pick a coordinate system. So in this case, the X will be downwind and Z will be pointing down into the water. And then we divide the directions into these little windows, are called quads for quadrilateral regions, and then 2 polar caps. And so what Hydrolight actually computes is the radiance averaged over each little window. Now there are other mathematical techniques where you might compute the radiance in an exact direction, and then you compute the radiance in this exact direction, and then if you wanted to average it, you'd have to take those values and interpolate and average and all this. Well, Hydrolight is simply going to give you the radiance averaged over this window, so some little delta theta delta phi, and then the average over this, average over this, average over the polar cap, and so forth. So it may print out a radiance and says the radiance at, let's say, theta is 0, 10, 20, 30, 40. Theta is 50 and phi is 90. It's not that exact direction. It's the little quad that's centered on that direction. And so then it takes as I said, it takes the radiance, it averages it over directions, it averages over wavelength bands. So you'll put in that you want to run it from, say, 400 to 700 nanometers by 10 nanometer bands. So the output will be the band averaged radiance from 400 to 410, 410 to 420, and so on. And then you'll save the output at some particular set of depths, let's say Z sub k. So you'll save the output maybe at depth 0, just below the surface, at 1 meter, 5 meters, 10 meters, whatever you want. So that's how you turn a continuous variable into a finite number of numbers that you can actually solve for on a computer. And any technique like Monte Carlo code or anything else, you have to take this continuous variable and some way discretize it and get a finite number of things that you're going to solve for. Okay, so that's the way that works. A few little comments about how Hydrolight works. If you are familiar with Monte Carlo simulations, the runtime for a Monte Carlo simulation increases exponentially with optical depth. So if you go to 5 optical depths and then 10 optical depths on the next run, that's not a factor of 2 in runtime. It's the difference of e to the 5 versus e to the 10, which can get really big. So a lot of people like Howard Gordon and George Kadawar and so forth, they have Monte Carlo codes. You'll never see them running them to 100 optical depths because it would literally take a year of computer time. Hydrolight, on the other hand, the runtime is linearly proportional to optical depth. So that's quite a big deal if you want to solve for the light field deep in the water. As I said, Hydrolight can have any depth profile of IOPs, and it really doesn't cost you any more time to have a depth profile versus just constant IOPs. There are other techniques, one's called discrete ordinates, that divides the ocean into homogeneous layers, and if you have to have 50 layers to resolve your depth profile, it then takes 50 times as long to run. I've already said it includes all orders of multiple scattering, and the good news is you can put in any inputs you want, and the bad news is you have to put in on the inputs. It doesn't know anything about your water body. And then there's various ways to do that. We'll see in a minute. There's a user interface where you're basically going to go through and answer questions and browse for file names and things like that. And then you can look at the output in various ways. And so I found with Hydrolight, just like with instruments, it's almost impossible to get people to actually look at the output. They want to just like click this button and draw a plot, and they never look at the printout where it says, oh, you know, your input absorptions were negative, you might want to clean up your data. But anyway, we'll learn more about that. And then how people use Hydrolight is, well, the nice thing about it is it's a controlled environment for you to play games and do experiments. If you go out in the bay here today, you're stuck with whatever IOPs are there and wherever the sun is in the sky and all of that. So if you wanted to study light fields as a function of many different water types, maybe you could do that over a course of a year, but you can't just control that yourself. But in Hydrolight, you can, you know, do a run and then you say, well, I wonder if the absorption had been higher or if the mineral particle concentration was different. What would that do to my light field? Could I detect that with a remote sensing signal? So you can play those kind of games. And then you may have data that you've taken of the underwater light field or the remote sensing reflectance, and you want to kind of figure out, well, what was going on in the ocean that could have given me that light field. So you can, once again, sort of do an inverse kind of study and figure out how could I have explained this measurement. And then, people use it for predictions, and they say, well, what if I did something and, I built a sewage plant here and it puts sewage in the water and then the phytoplankton grow, and then will that cause the light field to change enough that it would kill all the seagrass on the bottom? So people use it for that kind of thing. And then one thing we're doing here is teaching you a little bit of radiative transfer theory without having to spend 4 years on the mathematics to get there. So a bit of warning here. Hydrolight's a radiative transfer model. It's not a model about the ocean. So it's going to take whatever inputs you give it, give you back the light field. And if you actually put in the input, like the reflectance and everything on the optical properties of this wall here, it will compute the light field in the layer of paint and reflected by the paint and so forth. So it doesn't even know that you're running it for the ocean. It just takes your inputs and goes with that. And so you have to put in those inputs. And it's not idiot proof. If you put in some totally stupid kind of ocean input, it'll solve the radiative transfer equation and give you some completely unrealistic solution back. And that's either nice or it's bad, depending on your case. And I've actually had people ask me things like they get it and they start running it, and then it says, what's your chlorophyll value? And they say, I don't know. And I actually had a guy send me an email and say, well, what chlorophyll value should I use for the ocean? And, well, dude, you really shouldn't be running Hydrolight. You're not quite at that level yet. So anyway, that's all up to you, and it will do some checking of your input, so, but not a lot. And you do need to clean up your data before you get it. So here, for example, is an AC9 profile. This was taken in one of the previous classes at the University of Maine. So there's the AC9 is profiling. It's taking 6 measurements a second, and here's actually 2,056 AC9 values down to 25 meters. Well, the student took this and ran it through Hydrolight and eventually got an answer out, but that's not really what the ocean looks like. That's a lot of instrument noise. So you need to smooth your data, bin it, throw out the obviously bad values, etc., and come up with something like this. So here's 48 values binned, and I think it's a half a meter bins. So this is now something like what the ocean is doing. There's clear water at the surface and some chlorophyll, and it went down, and then here we're probably seeing some resuspended sediment right at the bottom. So this is the kind of thing you want to put into Hydrolight, not this, although if you give it this, it will do its calculations. Then in the same software, when you get to the end, it says, do you want to run Hydrolight or do you want to run Ecolight? Now, Hydrolight is computing the radiance in all these different directions. Ecolight starts out, instead of computing the radiances, it azimuthally averages the radiative transfer equation and ends up giving you just the irradiances and then the polar cap radiances. So if all you're interested in is an irradiance like ED, or you want the nadir viewing remote sensing reflectance or something like that, you can run Ecolight. If you really do need to know the radiance in this direction versus that direction, then you have to run Hydrolight, and it takes longer to run, but the answer is basically the same. So Hydrolight's going to solve for the radiance here. Ecolight solves for the azimuthal averaged radiance in a set of bands here, and so you'll see how that works. And Ecolight typically will run 30 times or 100 times faster than Hydrolight because it's not doing the same level of detail. And the runtime is actually proportional to the number of these little quads or the number of these bands. And the standard version uses 15-degree bands in phi, and so there's 24 of those bands, and the runtime is proportional to the number of quads or the number of bands squared, because you have to be able, for each light going into any direction, how is it scattered into any other direction? So that's why it's squared. So there's a big difference in the runtime. You'll just get a feeling for that. Okay, in the software package, there's basically this user interface that in the version we have here runs on Microsoft Windows. And you're going to run that. It's going to ask you all these questions about your input to define the problem. And then the interface collects all this information, passes it on to Hydrolight, which solves the radiative transfer equation. And then there's various kinds of output. There's what I call the printout, from the old days when you actually printed it out and looked at it. But anyway, this will have documentation of all the inputs and wavelength by wavelength, selected values for all the irradiances and K functions and reflectances and all of that. There's a set of files that are designed to be converted into Excel spreadsheets. There's other files that are designed to be read by the IDL plotting programs and so forth. And then, as I said, John Headley's been working with me to develop Apple and Linux versions, and we'll test those on you. And if he actually has the Apple version, not the Linux one here. And so if the Apple version blows up, well, we'll just go back to my Windows version. And if my Windows version blows up, maybe the Apple version will work. So anyway, the rules of the game here are that I have never received any funding for developing Hydrolight. So it's not like NASA or the Navy or somebody paid me to develop it, and now I'm screwing you for the money to get it. It's all been from day one an unfunded project. And in my directory thing on the IOCCG directory, there's a little PDF file called Hydrolight History. If you want to read this to see how it all came about, it goes all the way back to when I was a postdoc. And it's a kind of amusing story about bureaucracies as to how I got here. So anyway, you can read that and see how it all came about. But it's typical in science in the US that some scientist has an idea, they build an instrument for measuring whatever, and it works and people like it, and then other people want a version of the instrument, so they then turn it into a commercial product and let it pay its own way. And that's been the same story with Hydrolight. So it's copyrighted code. It's a product of the company I work for, and it's not public code, but it's freely available. And other people have codes that are just as good or better, but they won't give them to you. So so far, I'm the only game in town for things like this. Normally, when you license Hydrolight, you get all the source code and everything, because some people want to maybe write their own IOP model, or they want to reformat the output for just their output. And so if you have the source code, you can do that. We're not going to do that kind of thing in here. We have an executable version. And so some of the features of the full code are not in the executable. And there's features we just don't need here. So anyway, this code will run 500 times until the end of the class, whichever comes first. And if you do 500 Hydrolight runs in the next week and a half, you're going to be a real expert. But as I said, it's been around many years. Andre Morel, who used to be here, told me one time that he had done over 1 million Hydrolight runs. And so that was not one at a time. It was sort of making mass runs of 1,000 at a time or something. But yeah, it's been around a while. And the other day when I talked about this BRDF correction on the so-called exact normalized water leaving radiance, well, where he got that table of corrections was a lot of Hydrolight runs. So he would run Hydrolight, he would look at the nadir viewing water leaving radiance and the direction over here and figure out what number turns this into this. And that's what's in his tables, but it's really a bunch of Hydrolight runs. Okay, so you definitely need to go kayaking in Greenland. The Greenland It's all right. And I'm not a hot weather person. To me, it's just unbearably hot out here today. I need to have temperatures around freezing or below. And so that's why I go to places like Greenland. I've been there twice now, the first time in 2005, and I went back a couple of years later. And the first time I went there, flying into this little dirt airstrip on the east coast of Greenland, I thought, wow, I hope I see an iceberg. And well, we had to wait a day just to put the boats in the water because this was completely iced up. So anyway, yeah, I strongly recommend Greenland. I've never been to Antarctica, but I'd love to go, especially because in Antarctica there are no polar bears and no mosquitoes. So, okay, that's it for the little introduction. So let's fire it up here. And somewhere here, yeah, here's the student version. So I'll run exactly the version you have. And okay, so when you fire it up, you get this first window, and after you install it, you'll have to click on the disclaimer that, yeah, I know it's not perfect, and you know, there's a license agreement which you agree to, of course, because you'll never read it. And my license agreement is just copied off the back of the Microsoft license agreement, and I just changed Microsoft to Sequoia. So, and that was when I realized when you get software from Microsoft, like, you know, Windows Office or something, you don't own that software. Microsoft still owns the software. They're just licensing it to you to run. And it's like, wow, how many people actually know that? Okay, and then there's, you know, if you actually have the code, there's little things about, you know, where to find me when it blows up, but we won't worry about that. Okay, so the first thing you're going to do is define some kind of name. So let's call it, I'll just call this class run 1 or something. It says all the output files are going to use this little root name to identify them. So you might have Station 5, 22 July or something like that, but just a little one-word name, and then some little sentence that will go in each of these output files up at the top. So when you look at it 2 months from now, you can remember what it was. So this might be example 1 for IOCCG class, something like that. It'll just kind of tell me what it is. And so then the first thing you're going to do is have to define all the IOPs. And I've got 4 or 5 models here that are sort of standard IOP models. And your first homework problem, you'll use this when it says constant IOPs, they're independent of depth, and it's going to be only for one wavelength at a time. So let's just do a run there. It's kind of like your first homework. So you might put in that the absorption coefficient is, say, 0.2, and the scattering coefficient is, I don't know, 0.8. And so that's defined A and defined B. You have to pick a phase function. Well, there's lots of those guys. There's some that are built in, like isotropic. There's pure water. There's a thing called the Petzold phase function. Okay, maybe you want to use that one. Or maybe you want to have this Fournier-Ferrand phase function, which Zhongping Li or Darius or somebody mentioned, and you want to have a phase function that has a backscatter fraction of 2%. Well, you can put in the backscatter fraction, it'll go off in its database, pick out the right phase function and use that. So, and then even though this is at one wavelength, it needs to know what wavelength that is, and that's really for the sky model. You've actually already defined all the IOPs, but it still is going to have to get the sky inputs at some wavelength. Okay, so let's just do a run here, and here in a second it'll come up and it'll say, okay, you know, you can do all these other things. Well, notice there's a section down here that says inelastic scatter include chlorophyll fluorescence, CDOM fluorescence, and Raman scatter. That's been grayed out here. Why? Why can't I include fluorescence in this run? Right, there's only one wavelength. if I go back and I do a run and I say I'm going to use another IOP model and I'm going to run from 400 to 700, then I can include the fluorescence. But fluorescent light comes from this wavelength to this one, and if I'm only running this one, I can't compute that. So in this case, this model is only for one wavelength, so it says, sorry dude, you can't do that. You can put in a wind speed here, so that's going to define the surface conditions. There's some other things like having the index of refraction be a function of temperature and salinity, and we don't have that in your code just because it's an enormous big database and we don't really need it here. Okay, so then we're going to have to, well, this page is defining boundary conditions. So sea surface and then the sky conditions. There's a couple of options there. You can use a sort of semi-empirical model of sky irradiances and radiances, or you can use an idealized sky model. So let's just pick that one. And you could say, let the sky be, let's say, a heavy overcast, or you could let it be a uniform sky, and then we'll put the sun in one spot, and we'll let the solar zenith angle be at, say, 30 degrees, and the ratio of background to total is 0.3 or whatever. Or you can go back here and pick the semi-empirical model and say, put the sun at 30 degrees, or you can put in the latitude and longitude of Villefranche and that it's 9:37 a.m. on July the 21st or whatever, and it will then compute the sun angles for you. So various ways you can do that. You can have a cloud fraction from 0 to 100%. So 0 is clear, 100% is a thick overcast. You can't put in this version, a cumulus cloud here and one here and clear in between. You can do that in the latest version of the code, but that's a different story. You can pick, if it's a specific day of the year, the sun's irradiance varies by about 8% over the year, and you can actually, if you put in back here, whoops, oh, I screwed it up now. I killed the code. If you put in a particular day of the year and so forth, so let's say class 1, example 1 for class. I just hit the wrong button. Okay, so let's just do this again. I don't know, point 2 and 0.8, and let's say we're going to run the Petzold phase function, and then we're back here. So if you had come in here and put in a specific time and location, then it would know the Earth-Sun distance on that day, but we'll just use the annual average here. Okay, and it's going to use this model called RadTran X to compute all this sky stuff. There's also options where if you have measured the input sky irradiances from a DEC cell during your experiment, you can put those on a data file and read them in, and we'll talk a little bit about that in the second part of today. And then you can run the water column as infinitely deep, or it can have a finite depth. And if it's a finite depth, then you have to say, something about the bottom conditions. So let's just say we're going to let the water column be infinitely deep. Okay, then we have to tell it, what outputs do we want here? Okay, let's run it down to, say, 20 meters, and we'll let the output be every 5 meters. Now, this has nothing to do with solving the equation. It's just the radiative transfer equation. It's just where you save the output to look at later. And, this depth could be either meters or it could be optical depths. So let's say we're going to use 20 optical depths. You're going to do that in your first homework problem. And then there's various kinds of output you can save. There's a couple of files that are generated that you can use in Excel spreadsheets. You always want to save what I call the standard printout, because that's going to have any error messages in it, and it's going to sort of have all the inputs and outputs that you can look at later. So I always save that one. If you don't ever want to deal with Excel spreadsheets, you don't have to create those files. There are other files here that are for processing in IDL, or some people use it with MATLAB, but I'm an IDL person and you guys are probably MATLAB people, but they're basically the same. There's also, you can generate a file that has all of the radiances. So there's just basically a big column that says depth, theta, phi, wavelength, radiance. And you know, if you want that information, you can create it. That can be a very big file if you're saving output at 50 different depths and 50 wavelengths. It can be tens of megabytes. So most people don't want that, but some do. So if you want it, you can create it. Okay, so then as I said, and you can also click here now and save all of these inputs, so the next time you go through the front end, you don't have to enter all the information again. Maybe you just want to change the sun angle or something like that, then, or the chlorophyll concentration, and you can do that. So now it says, do you want to run Hydrolight or do you want to run Ecolite? And I'll just show you this file here. All the front end has done is collect all of your answers together, and it writes a little file with file names and wavelengths and so forth, and then it gives that file to Hydrolight to run. And at that point, the front end has nothing to do with it. So some people, they will throw away this front end and create their own input files, and then they run Hydrolight on a Unix machine or something. And that's fine, you can do that. We're not going to worry about it in here. So, okay, let's say we want to run Hydrolight, and we'll just click the button, and it'll come up here in a second, and it's running, and that only took a couple seconds because we were only running one wavelength. Okay, so let's look at some output before we do anything else. And now, because it has redone my screen, well, let's just open this up. And normally there's a bunch of things down here that I can, oh, I bet this is it. Yeah, here we go. There's what I wanted to see. Okay, so after you install this, you'll have, let's see, where is it here? There's you actually have version 5.2. So there's the version we're actually running, and this will be somewhere on your computer. Okay, so quick look, there's a directory that normally has all the source code in it. There's a directory that has data files for bottom reflectances and phase functions and surface files and all this. When you have your own data, stick it in this user directory, and when you get to the homework, you're going to use these couple of files here. And I just noticed the other night, yeah, that one's okay. Sometimes this AC9 Bahamas file will say 4 kilobytes, and that's because it got garbaged. This one says 2 kilobytes, so it's okay. But what's on the CD here may be the 4 kilobyte. You try to run Hydrolight, it says I can't handle this file. We'll fix that later. I put this file on my directory there, so you can download it from there. But anyway, these things have, here's files of phase functions with all of these Fournier-Ferrand and so on. And so, Petzold phase functions for clear, coastal, and harbor water, all those kinds of things are in these data files. We don't have to worry much about that. There's a documents directory. There is a detailed user's guide that says, here's how to sit down, install the code, do a run, look at the output. There's a technical documentation that if you want to know really how does this case 1 water model work, or how does the sky model work, or whatever, it's all in here. I can guarantee you from 15 years of user support that no one's ever actually looked at the documentation. So, but it's here if people want to take a look at it. And it's on here as PDF files as well. And then often I'll get, a question from somebody about how does Hydrolight do the sky part, or how does it compute Secchi depths or whatever. And 3 weeks later, I'll figure out the answer, and then I'll often write up a little technical note on something like how it does the surfaces, or how it does sources, or how, you can get some very confusing things when you look at, let's say, a radiance above the surface and below the surface, and the radiance is greater below the surface than it is above. And people say, well, wait a minute, the sunlight's coming in, part of it's being reflected by the surface, so how can it be bigger below the surface? Because that violates conservation of energy. Well, it's conservation of energy, not conservation of radiance. So there's little factors of index refraction squared and all that. So I'll often write up, some little kind of note thing here about whatever it is, and those are in there. So anyway, you probably won't want to look at them in this class, but they're there to play with. There's when you get the code, you get a bunch of example runs which you can reproduce on your computer and make sure everything's working okay. The front end is just the user interface. So when you install the code, depending on your operating system, it may stick an icon on the desktop, or maybe it doesn't. And if it doesn't, you go here and it's this HE5 Windows User Interface.exe. You can make a shortcut to that and put it on your desktop. Then what's really relevant here is the output. So in the output, there's an Ecolite directory and there's a Hydrolight directory. So I think we just ran Hydrolight. So then there's a file that contains these digital files that are for use in like IDL or MATLAB. And if you look here, there's one called D for digital file, and class 1, that was that little name I cooked up right at the first. There's this L file, that's the radiances, big table of radiances. There's the files for the Excel spreadsheets. And so there's a multi-wavelength version, and what that does, as we'll see in a minute, is each page of the spreadsheet has one quantity, but all the depths and wavelengths. And then there's a single wavelength version where each page of the spreadsheet has several different quantities like absorption, scattering, attenuation, etc., but it's in blocks of one wavelength at a time. So just depends on whether you would see a lot of things for one wavelength or one thing for all wavelengths on a particular spreadsheet. And we'll look at some of those. And then there's the printout files. So there's our printout for this run. And let's just look at that. Okay, so when I recommend, at least to start, when you're learning the thing, you always look at the printout. And if anything weird happens, you look at your data and it's like, wow, this doesn't look, or you look at your output, it's not really data. And you say, well, something's not quite right here. Look back at the printout, and well, you may discover you put in a chlorophyll of 3 and you meant to put in 0.3, something like that. Because you look through here and it'll say, okay, I'm solving at these theta 5 values, I'm solving at these depths, or saving the output at these depths. And I used this IOP model, was the AB constant, absorption was this, scattering from this, the phase function was from this Petzold average particle, and okay. And then here the chlorophyll fluorescence and so forth were not included. There's some info on the atmospheric specification. So the sun was at 30 degrees, the relative humidity was 80%, et cetera, et cetera. And then, the wind speed was 5 meters per second, the bottom was infinitely deep, and it says homogeneous water below optical depth 20. So that's worth commenting on what's going on there. So here's, let's see here, whatever's going to be the, yeah. Okay, so here's an IOP, so absorption or scattering. Here's depth. Okay, so when you, let's say you have AC9 data and you went down to 50 meters with your AC9. Okay, so, and then you started it at 1 meter below the surface. So you might have this profile of absorption. And so this is maybe 2 meters, and this is 10 meters, and 20 and 30 and so forth. Okay, so there's your real ocean. And you're interested in remote sensing reflectance and you don't care about anything else. Well, in principle, what nature does is it takes this profile and it runs it all the way down and it gets the remote sensing reflectance. Let's say that you say, look, I don't care what's going on at 50 meters. I'm just going to run Hydrolight down to, say, 15 meters. So that's this value here. Well, what Hydrolight does is it takes this profile down to 15 meters. And you said make the water infinitely deep, but you only ran to 15 meters. It then takes this last value and assumes the water is homogeneous below that depth. So you're really solving for this ocean, not for the real one. Now that may be just fine for computing remote sensing reflectance because the light at 15 meters doesn't affect the remote sensing reflectance anyway. So that may be perfectly fine. You just have to keep in mind that Hydrolight does some things like that. And then up at the surface, if your first AC9 value was at 2 meters, well, Hydrolight needs to solve from depth 0 on downward. So it's going to take this value and assume the water is homogeneous up to the surface. Now, the real water body might have looked like that, or it might have looked like that. So that might or might not be important in your particular water body. And the only way you know is start your measurements here, not at 2 meters depth. So there's some things like that it does, and that's why it's printing this little warning that says, the bottom's infinitely deep, homogeneous water below optical depth 20 or whatever it was. It's just kind of warning you that, you know, I stopped here and then I had to make the water homogeneous below that in order to compute the reflectance of this infinitely deep bottom below me. And then I may have saved the output at, say, you know, every meter or something, and so the light field will be saved at these values here. Okay, likewise, if we take, here's wavelength and here's IOP, so here's your AC9 data, looks like this. So here's 412, the 443 value, maybe you have one at 488, whatever, and out to 720 or whatever you have on your instrument. So there's what you actually know for the IOPs as a function of wavelength. And when Hydrolight starts running, it may be at, you know, wavelength 470. So it needs to know the IOPs there. So what it'll do is it'll take these values, linearly interpolate and say, okay, I know the IOPs there, I know them there, I know them there, I know them there, and then it'll interpolate. So it's really solving for this profile in wavelength of IOPs. Now, you can start the Hydrolight run at 300 nanometers, and it'll work just fine, but just like here, it doesn't know the values here, and it doesn't know the values less than 400. So if you start the run back at, say, 300 nanometers, it's going to take this value and just make it the same all the way back to 300. So you can do that. It'll print out a little message in the printout that says, hey, you know, your first real input was at 412. You probably shouldn't trust the values back at 350. And if you want to really get good values at 350, you need to measure the absorption coefficient down to 350. And, you know, well, you say, but I only have an AC9 or an ACS and it doesn't go to 350. Well, you know, what can I say? That's not Hydrolight's fault. You need to talk to your friendly instrument manufacturers and have them put out an instrument that will measure IOPs down to 200 nanometers and out to 2,000, and then you're good to go. Okay, so anyway, this is the kind of stuff that's in the printout, and then it gets down here and it says, okay, output for wavelength band 1. Well, in this case, it was really just a 1 nanometer band, but there will always be then little tables of absorption coefficients. In this case, there's only one, which was the total. In a minute, we'll see, it'll say like component 1 is pure water, component 2 is chlorophyll, 3 is CDOM, 4 is minerals, etc. But there's that kind of information. These little tables will be there, and kind of summary tables. There's something called the asymptotic radiance distribution that we haven't talked about. Then there will be a table of irradiances. So here's, as a function of depth, there's scalar upwelling, scalar downwelling, total scalar upwelling plane, downwelling plane. I briefly mentioned these mean cosines. There's our irradiance reflectance, and you can see, you know, it's sort of like 3%, typical number. Mean cosines tend to be, you know, the downwelling part's usually somewhere around 0.7 or 0.8, and upwelling's maybe 0.3 or 0.4. Yeah, that looks okay. Here's all of our K functions here, and there's a different K function for every radiometric variable. So there's KD and KU and K scalar and K for LU. Notice they're all different up at the surface, and they all come together to the same value as you go down deep enough that the surface is not affecting you. Okay, then there's tables of radiances in selected directions. So if we look here, I've got theta and phi, which are the direction the photons are going, and then the phi view, it's the direction you would point your instrument. So if I'm looking at you know, a 10-degree theta angle and phi of 0, that means the photons, well, actually 10 degrees is down here because we're measuring from the depth. So that's light going that direction, but you would point your instrument in this direction to see, if I'm looking upward, I'm seeing the light coming down. It's always confusing on these coordinate systems, even for me after 40 years. And then there's the sky radiance looking in a particular direction. There's the water leaving radiance, the reflected sky, the total upward. There's probably what you really want, which is remote sensing reflectance. And notice it does depend a little bit on the exact viewing direction. And the downwelling direction here, the very first one, that's the one that most people call the remote sensing reflectance. But it does depend on angle and our direction. And then there's, what's this? Yeah, this is the radiance in selected direction. So the light coming upward, the light going downward, and the light horizontally looking towards right angles and away from the sun. Just a little quick look at those things. There are other things you may have heard of, Q factors and so forth, that we'll probably not talk about in here, but they're there. And in this case, we only had one band, one wavelength, and it gets down here and it says PAR was not computed for this run. Well, PAR is a broadband measurement. We have to run at least from 400 to 700 to compute PAR. So it didn't do it. So let's go back here and do a little better run. So it says define a new batch run, and let's just call this one class 2 and example 2 for class, and it might be new case 1. Whoops. Okay, so if I get to here, here's what I call the classic case 1 IOP model. If we just look at that real quickly, well, actually, it's back up. It says component 1 is pure water, component 2 is chlorophyll varying particles and co-varying CDOM and non-algal particles. That's the definition of case 1 water, is that the optical properties are determined by chlorophyll and its co-varying CDOM and detritus and so forth. Okay, so you can pick this model. It says absorbing and scattering values are from this default seawater file. If you're working in a lake, you can pick freshwater values. There's another set of data called Smith and Baker's clearest natural waters. Most people will use the Pope and Fry seawater for the ocean, but if you've measured pure water values and you think yours are better, fine, you put them on a file, you read them in. we'll look at how that's done later. So then I can put in a chlorophyll concentration. It could be constant with depth. And then I could have a file that has chlorophyll as a function of depth on it. And so any input like chlorophyll concentration, mineral concentrations, sky irradiances, AC9 data, whatever, there's always a standard format file that if you put your data on that file format, you can then read your data into Hydrolight. And we'll look at some of that a little bit later when we do things like that. But for the moment, let's say we just wanted a constant chlorophyll of 0.5, we could pick that one. We could pick the phase function with, say, maybe let's say, 0.5% backscatter, sort of typical of phytoplankton. And so we could do that. And now we're going to run an IOP model that's generally for more than one wavelength. So we can say, yeah, let's include chlorophyll, CDOM, and Raman scatter. And then it says, okay, I'm going to get the chlorophyll from the number you gave me, it's constant with depth. If you'd read in a file, it would say, I'm going to get chlorophyll from a file named such and such. So you can kind of look at that. The CDOM will be calculated from the chlorophyll in accordance with this case 1 water model, where the absorption by CDOM at 440 nanometers is like 20% of the total and so on. And that's all described in the technical document. And then it says you must include the relevant excitation and emission wavelengths. So you might want to, if you're really interested in 400 to 700 nanometers, you might want to start the run back at 350. Why? Because the light at 400, when you include inelastic scatter from Raman scattering, that light is coming from all the way back to 350 or 360. So you need to go back there to make sure that the inelastic scattered light is there at 400, even though when you get done with the run, you may ignore the values at 350 because you were really only interested in 400 to 700. So there's just little warnings like this to make you think, yeah, is this really what I wanted to do? Now we can do, well, first of all, notice now there's no opportunity to do a single wavelength run. How come? Any guesses? Why can't I just say, okay, I just want to run this at 440 nanometers? Yeah, because we included inelastic scattering. So it's, you have to run it at multiple wavelengths. So, okay, now if I go back and I unclick the boxes for running, or for including fluorescence and Raman scattering, then it'll let me do a run at one wavelength. Okay, so let's say we'll do a multi-wavelength run, and let's say 400 to 700 by 10 nanometers. And this can be anything from 300 to 1,000. And keep in mind that each wavelength costs you sort of the same amount of runtime. So if you do 400 to 1,000 by 1 nanometer, well, that's going to take a long time. But you don't need that level of information anyway in most cases. So, okay, let's just go with that. And, maybe the wind's a little stronger today, so I'll put in 10 meters per second. Or maybe you think in terms of knots or something, so you could put in, 20 knot wind, and that's really 10.2 meters per second. Okay, so semi-empirical model there, let's go with that. We'll just leave that. If you do want to change the atmospheric parameters for things like ozone concentration, precipitable water, all those things, you can do that in there. There's an air mass type where 1 is open ocean marine aerosols through 10 is, continental dusty smoky aerosols, but most oceanographers are happy with the marine and they didn't measure that anyway. So, okay, so let's come down here. We'll just use the average, annual average. We'll use RadTran, and let's let it be infinitely deep again. And I don't know, let's go down to 30 meters, and then yeah, save the output every 5 meters. If you want to save it at irregular intervals, let's say you want to save it at 0, 1, 2, 5, 10, 15, 20, and 30, let's say, you can put in a list of values there. Okay, let's just save that for the next run, and let's run Hydrolight. Okay, so this will take basically a couple of seconds per wavelength here.
If the excitation bands are like don't match these intervals, you may miss from a scattering, or I mean, suppose there's a band in 520.
Yeah. So what it's going to do is, if we look at the wavelengths here again, so let's say you had AC9 data, and this was 412, 443, whatever, and you're now running at these 10 nanometer bandwidths. So they might look like this. So what it'll do is it picks out the IOPs at the middle of each band here. And so that's where it gets its IOPs. So they're really not quite band averaged values. Now the sky irradiance, if we look at ED for the sky, it's actually in there at 1 nanometer resolution. So in the band here from say 440 to 450, it will actually average this 1 nanometer data and get a band average sky irradiance. And then it'll print all this out as being, and calling it 445, so a halfway point there. So that's how it kind of does things. Does that answer your question, or?
Yeah, in the case of the excitation bands,
yeah,
the inelastic scattering, it's
yeah, you know, basically what it's going to do is, let's say for this band, it has been looking back here at the, it takes the band averaged light field here, let's say this is 350 to 360, 370, and so forth. It'll take this value that it computed band average from 350 to 60, and it'll plug that into the Raman equations and so forth and find how much is scattered from this band over to this band. And then it'll take the value at 365, plug that into the Raman equations, the chlorophyll excitation spectrum, et cetera, and figure how much is scattered over to here. So it's always working with these band average things. And for most purposes, you know, 5 nanometer band is hyperspectral imagery. 10 nanometers, you know, good enough. Like AC9s have sort of nominal 15 or 20 nanometer wide bandwidths. And, you know, an ACS is sort of like 4 nanometer wide bandwidths. So somewhere around 5, 10, or 20 nanometers is what you normally use. You don't need 1 nanometer unless you're doing something really special, but you don't want to use 50 nanometer bands either, because then you've really gone too crude. Okay, so Hydrolight ran, and that took I don't know, whatever, 2 minutes or something. Let's just do the Ecolite run. It's got exactly the same inputs, but you'll notice it runs faster. So these are taking like 1/10 of a second instead of a couple of seconds, and that's because it's solving a different radiative transfer equation. Okay, so if we look at this output in a little more detail, so, okay, so there's the printout for class 2, or, you know, the name of it, and same stuff as before, you know, what went into it. Now it says I'm using this AB case 1 model. And component 1 is pure water, then there's pigmented particles, and then there's CDOM that varies with chlorophyll. So there's really 3 components in there. And then if you look down here, okay, the chlorophyll there was constant with depth. And then, you know, it says Raman scattering and so forth were included in the run. And the sky information, the wind was 10.2 meters per second. The bottom boundary infinitely deep, homogeneous below 30 meters in this case. And then it sort of starts these blocks of code. So here's wavelength band 1, 400 to 410. Here's the absorption for pure water, chlorophyll, CDOM, scattering, etc. Here's the totals. Here's then, you know, the irradiances and so on down, and then you get to the output for wavelength band 2, and it's just the same info. And then finally you get down here, and now at the bottom it says, okay, here's the scalar irradiance in energy units as band integrated values. In Hydrolight, the radiances and the irradiances and so forth are generally band averaged values. So irradiance is watts per square meter per nanometer, as opposed to integrating over the band of, say, 10 nanometers wide and getting watts per square meter in the 10 nanometer wide band. But down here, because people who are doing ecosystem modeling, for example, they need to know how much irradiance is there in my 10 nanometer wide band. So I actually put out a little table here that says, you know, watts per square meter values are integrated over the wavelength bands. And then the same thing in quantum units, micromoles, photons per square meter per second. And then because we ran from 400 to 700 nanometers, it can compute PAR. So here's the PAR profiles. It's sort of like 2,700 in the air, 2,000 in the water, going down to 150 at 30 meters depth. So if you're an ecosystem modeler, that's what you're really probably interested in. A lot of people compute PAR from ED, which is really not correct, but they do it. So I put in what would have been the PAR value if I'd used a plane irradiance sensor to get PAR instead of a scalar irradiance sensor. And you know, 2,700 versus 18, that's a pretty substantial difference. And then some people have ecosystem models that use broadband PAR values, so there was actually 402 watts per square meter over the 400 to 700 nanometer range and so on. So there's output like that. There are things called chromaticity coordinates that tell you what color the water is. There's a thing called the Forel-Ulla number that's a measure of water color. It goes from like blue to green to yucky brown. And so you can look at this, and a Forel-Ulla number of 3 or 4, that's very blue water. Well, that makes sense because we put in a chlorophyll of 0.5, so that's a typical ocean value. If you put in a chlorophyll value of 10, this number is going to be 10 or 12 or 15. Okay, so anyway, this run took 75 seconds, basically. So there's that. Now, if we go back up, let's go to the Excel directory here. And here's a Excel spreadsheet. It's called multiwavelength.xls. So what that is an Excel macro that will start that up, and then we can open these M things, M for multi-wavelength. We can open these files with this macro, and then we're left with an Excel spreadsheet. So let's just fire that up. And at this point, of course, okay, so we're actually looking at this macro, which you don't really see. You go to View, and this depends a little bit on how new or old your computer is. Are you running, you know, Windows 10, Windows 7, whatever. But basically on this computer, you go to View Macros, view the macros. There it is, macro multi-wavelength. Run that guy, and it says select the mroot file. So here we're HE52 output Hydrolight Excel, and oh no, sorry, that's my, let's see, that's the regular version. Let's browse down to the HE5 for the IOCCG class, and output Hydrolight Excel. Okay, so there's our 2 runs we just did. So let's pick this guy, open it up, it crunches around, it does weird things, and then it says, do you want to save the Excel workbook? Sure. Now at this point, about half of you, it's gonna, or maybe all of you, it's gonna say Excel macro, no, not allowed, can't do that. And some of you, you can click a button that says, I trust the guy, go ahead and run the macros. Others will say, you must have administrator privileges or something, and contact your IT professional. Well, figure that one out. And then some of you may have your computer set up to where it doesn't care whether you run macros and open zip files and all of that. So we'll just see what happens. Okay, so anyway, at this point, we now have a spreadsheet that's just in Excel. It's nothing to do with Hydrolight anymore. So you'll notice here's absorption, scattering, backscatter fraction, ED in the air, E0, ED, all of these things, and it goes on, Ks and pars and remote sensing reflectances and all this kind of stuff. So, for example, if all you wanted to look at was remote sensing reflectance, well, there it is. And there's the remote sensing reflectance versus wavelength. There's the ED and the LW that went into computing that. And then there's also the total radiance above the surface. So you could just do something, you may have to knock that out. You can just come here and say block that out, and then say insert a figure here, and boom, there's your remote sensing reflectance, and for this particular run. And it never ceases to amaze me that in 40 years or whatever that Microsoft has been making crappy software, they cannot figure out that if we look at this guy's data, it goes from 400 to 700. So why don't we make the x-axis from 400 to 700? No, it always starts from 0. And so then you have to go in, of course, and play these games, reformat the axis and start at 400 and stop at 700, not 800, and on and on and on. Whoops. 700, and you can clean things up. And this is why I never use Excel for anything except demonstrating to students that you can use Excel. Anyway, when I first started in the game many years ago at the Jet Propulsion Lab, when I walked in the door, they said, okay, IDL is the official graphics package for NASA and for the Navy. Here it is, learn it. So that's why I got in the IDL path. If you're a student and you walk into university, today they say MATLAB is the thing to use and you learn MATLAB. But they're basically the same thing, and they both, they charge outrageous amounts of money every year for their so-called user support. Okay, but at any rate, here's this, spreadsheet, and you can now do whatever you want with that. And if you want to look at, let's say, let's go over here. So here's, here's, let's say, the ED. Okay, now here's ED in the air and as a function of depth, and then at all the wavelengths. So you can take that, and if you want to just do a quick look at it, there's all the EDs in the air. Depth 0 is just below the surface, and then 1, 2, 5, 10, all the way down to 30 meters. Okay, so you probably all know how to use spreadsheets, so go to it. And then we could also look at this single wavelength spreadsheet. So if we go back to Excel, and there's one called single wavelength, so let's just pick that guy. And once again, we'll do the view macros. There's the single wavelength macro, run that. And there's the single wavelength for the class 2 thing, so we'll open that. And then what you'll see is like, here's a page called IOPs. So there's absorption scattering, beam attenuation, albedo of single scattering, backscatter fraction, and then here's wavelength 405, wavelength 415, 425, etc. So there's little blocks that are one wavelength at a time. But this spreadsheet is the same information that's on the multi-wavelength spreadsheet. It's just organized differently. And there's some things that are not here that are on the other, but basically it's the same thing. Okay, so that's kind of it. I think what we might as well do is take the break now and let me pass out these things. They're all the same, so just pass them around. There will no doubt be something horrible happen on some computer. For example, the default is it will install it to your C drive. So like it'll be C/HE52 da da da. Do it that way. Last time somebody installed it to their desktop and it ran fine, but the output disappeared and we never figured out where the output went. So they just uninstalled it and reinstalled it to the C drive, and everything is there. So ask Bill Gates, I don't understand it. So anyway, we'll take a break. We'll come back at, 11 o'clock, and by then we will have probably been able to install it on enough computers that you can pair up and run the thing.